we have drawn a Lewis structure of ClF3. So that's, I believe, chlorine trifluoride. And we want to identify the number of bonding and non-bonding electron pairs. And what's the electron pair and molecular geometry of this molecule. So Lewis for ClF3. Okay. So with this being said, we have all of them are on the same column. So really it's going to be 4 times 7 valence electrons. So what we're dealing with is 28 electrons total we have to work with. And now for this, because chlorine is a unique one, we'll put it in the middle. Even though they both have the same amount of unpaired electrons, chlorine is the only unique one in this case. So we have Cl, and then we somehow have F3. And you're probably questioning already, how are we going to do this? Because chlorine only wanted one bond, really, because it's only missing 1 electron to have its octet. So I'm going to tell you right now, chlorine is indeed going to break the octet rule. It's going to have to expand. So with that being said, let's fill this out in regards to it. So we have, oh, maybe that's not an L. This is an I, which does change things. The reason why, because as I was doing this, based on this, if I were to draw it out, okay, and I had the F's will be balanced out, but the issue with the chlorine is that's sharing 3 of its 7, so it'd be 4, 5, 6, 7. Oh no, it could work as well. Well, we have to make a casting call here and just assume we're talking about chlorine trifluoride. And I'm going to put carbon as well. That one is just relatively straightforward, where it has the iodine and the 4 fluorines. That works as well. But let's just assume it's chlorine trifluoride. So let's try again. Okay. So, with this being said, we're going to have 1, well, technically it's sharing 1 of its 7. So 2, 3, 4, 5, 6, 7. Same thing here. 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. Okay. And now the chlorine in the middle is sharing right now 3 of its 7. So it's going to be 4, 5, 6, 7. So that is what chlorine is looking like right now. Okay. So with that being said, it's asking us for the number of bonding and non-bonding electron pairs. Before we do that, let's just make sure this is correct. As we said, we want to work with 28 electrons. Do we have that? We have 3 bonds, that's 6. And then how many lone pairs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11. So that's 22 electrons, because lone pairs have 2 electrons each. So 6 plus 22 is indeed 28. Now we also have to see if this actually does satisfy the, well, not the octet rule, because chlorine is clearly breaking that, but the formal charge. So fluorine's formal charge of net of 0 is typically drawn as 3 lone pairs and 1 bond. That is what every fluorine has. Now chlorine would typically be the same thing, where it has 3 lone pairs and 1 bond. But with this expanded octet, what we could do is that each of these electrons in a lone pair could be turned into a bond. So this is all we're going to do here, because to match the picture, we do indeed have 3 bonds and 2 lone pairs, which is what that chlorine has. So everything here does have a formal charge net of 0. So we're good to say this is yes. This is our Lewis structure. Now let's identify the number of bonding and non-bonding electron pairs. We have, based on the central atom, 1, 2, 3 bonding pairs and 1, 2 non-bonding electron pairs. Okay. So with that being said, the way we would write this down is that it has a 3-2 split, So the total of this, in terms of how many pairs it has in total, is just going to be known as 5. That's how we're going to find the electron pair geometry, okay? So with this being said, if I remember correctly, the hybridization for this would be sp3d, and this electron geometry, so the EG, is known as trigonal bipyramidal. If I know how to spell pyramid, bipyramidal. There we go. So that would be that name. Now, because it's a 3-2 split, the molecular geometry actually, this one is known as T-shape for the molecular geometry. What I mean by that is that because the lone pairs, it's kind of going to do this. It's going to be one on the top, one on the bottom for the chlorine, and they're going to have 2 electrons, and then this is going to stick out like that. Theoretically, this would be the most, I guess, the best structure for it. So if we looked at it at a plane, this is the x-axis, this is the y. The electrons and the fluorine would kind of be on this x-axis, and then the 2 fluorines will stick out on the y-axis. So that's how we kind of have this T-shape, because it kind of goes like that. Okay? That is what I believe, and we're going to actually double check here in regards to the Vesper theory that we have. So we have 3 and 2 split. It is 5, so the bonding groups is 5. Let's scroll down. Electron groups 5, and it is a 3-2 split, and it is indeed known as a T-shape, what looks like that. So that's perfect. Okay. So with that being said, let's see actually if we can agree with our colleague as they draw it. So it was indeed chlorine trifluoride. So that's good that we didn't try to solve for carbon. And with that being said, the 5, they do say it's trigonal bipyramidal for the electron geometry. And it does say that it has a T-shaped molecular geometry. So this is correct indeed. So let's move on to question number 9.